Hello everybody, it is Sam the Reclaimer developer, and welcome to another devlog for It Flies By. Last time we talked about memory management, but I've never really seen too many videos on like the concept of custom allocators. So like, we talked about what the concept of an arena is, and so basically how we have our virtual memory that we are just gonna partition and divide into hierarchies, and like each engine system is gonna be inside of, you know, some of those hierarchies and just having their own sandboxed region of memory to play with, and we're gonna be going into how do we actually take that memory and divvy it up. So when you see the code, it's going to be in a different state than when I was recording last time. This isn't like Handmade Hero, where every single line of code is written live. This is going to be a bit different. One, I'm not as experienced as Casey Muratori, and just second of all, sometimes I like to take the design of things offline and just come back to it when I can. And also, I just do not have a consistent schedule right now. It has just been a bit crazy here at home. Like I said last time, people coming out of being sick, and just other things. So with that, we're gonna just sort of quickly do a refresh on like the memory architecture. So I'm gonna do this. So like we have our memory context, right? This is what I'm calling it. And this is what we initialize at startup, right? So this is going to be managed by the game engine itself. And the context is divided into two parts, two primary parts. We have the stack, and we have the reservation. So the stack is pretty straightforward, right? So what that looks like is we just have a fixed region of memory, and there is a, like I think in this case, what I've decided is I'm going to make the stack size 512K kilobytes, right? And so basically we have 0, where it starts at the bottom, and there's like some address, right? This will be 0x, you know, some value that represents a pointer down there. And what we can do is we have this position. And as we commit stuff to the stack, what we do is we just return this position as an offset. And so now what we've done is we have just made this indexable by an integer. So like this right here is just going to be an unsigned 32, right? And we just return that as a our handle to get something out of the stack, right? And there's more that I want to go over in regards to that, but that's just the crux of how it works. And this is mostly for singletons, right? AKA single instance objects, right? And this is just another way of saying there are objects that are allocated where that are somewhat small, but there's only one of them throughout the entire lifetime of the program, right? And so things like this would be, you know, the objects or structures to systems like the renderer, the graphics manager, window, game window, user input, and things like that. So there's not going to be more than one of any of those things going on. So we just basically push it onto the stack. And so normally in a diagram like this where you're going over how program memory is divided up, and sorry, I have this curtain back here, and my dog is currently destroying everything that I own. Sorry about that. There was a I put a Valentine's gift together for my wife, and there's some like leftover like cardboard like material and stuff behind this curtain. My daughter was in here playing. It was a snow day here in Kentucky, so this entire room just looks like a tornado right now. So thank God for this curtain. But I'm trying to get it to look nicer, but yeah. Anyway, so what we have is a reservation, and this is what we use instead of a heap, right? Because the heap is slow, it's prone to corruption and fragmentation. So instead, what we do is we just have this big reservation of virtual memory that we make on program startup, and the reservation is divided into arenas, right? So we have like I'm just gonna say a sub 0, a sub 1, a sub 2, all the way to a sub n. And there may be like empty space, like, you know, on the other side of this that, you know, we didn't get to, but it works in similar ways to a stack, right? So what I do is, like, a reservation also has a position. Very similar to the stack so far. But what these are is these are committed regions that are mapped from RAM directly into our program's address space, if I understand the concept of virtual memory correctly, which it's possible that I don't. But we'll just say this right here is an arena. Arena, if I can spell, which I'm an engineer. That doesn't mean I can spell. I code. I don't. I engineer. I know can't English. Right. So, and an arena is just you know, AKA sandbox. And it's just it is a predefined area of memory that is committed, and so we just commit these arenas on startup for, you know, whatever system needs them, and they have a start and an end. And what we do is we say, hey, Mr. Arena, give me a pointer at this position. And so it just returns the pointer. And so we can just have a, you know, an opaque handle to these things. And if we put the actual, like, struct onto the stack over here, then that means our arena itself also can become an opaque handle, right? So there was something else that I wanted to go over, I believe. But this is sort of the, I guess, the high-level overview of our memory architecture, right? So, and so where we are today is like, what do we do with an arena? Oh, now I remember. So let's go over some terms again, right? So, and this will help us understand how to break up an arena, right? So, let's see, managing, that's a horrible M, managing arenas, okay? So, and this is sort of like a refresher, but there's some terms that we need to understand, right? So the arena, we'll just, again, say sandboxed region, right? And so reserve, instead of like, we have like reserve and release, right? And this is just a replacement for new and delete. You could also say malloc and free. So basically, how how this usually works is it alternates between reservation. It's like I want to reserve something, I want to commit something to that reservation, and then inside that commit, I may reserve some more things, and inside of each one of those reservations, I have more stuff that I commit. So, but the point is, a reservation is temporary, right? As in, it has a lifetime, or a contextual. It has a contextual lifetime, right? And then I have commit, right? So what's the difference between reserve and commit? So commit is, it's fixed, right? / constant for contextual lifetime. As in, like, let's say if I have an allocator or something I pushed inside of an arena. Like, I can't change the fact that I committed something to it, but when I release the arena, or if I just, like, clear the, like, release the allocator, then everything it was managing goes away like that. And that's really... And remember, we're not really working with pointers, we're working with offsets, right? Like, we can get pointers using offsets, but we don't have to store them. Like, storing pointers should only be done when necessary. So there's a few that I store, like, in linked lists and stuff, but, like, the key to getting that linked list may be just an offset inside of an arena or something. And so now I want to talk about some, like, terms to append to this. So, like, postfix, like, reserve, release, commit, right? And so that is relative and absolute, right? So let's bring back the concept of a stack, right? So you have start, end, position. Okay? And so basically you have this stack and it goes up, right? From start to position. And absolute is a pointer. Okay? For example, like, it would be pointer commit absolute. Okay? And so relative is an offset. Right? And so I just return a integer that is how far away from the start position is it inside of this data structure, right? And it doesn't just go for arenas, it goes for allocators, it goes for arrays, lists, queues, basically any data structure that you can think of. Because a data structure, in the context of it flies by, it has a start, address, and a size. And so from that, I can derive, the address space of everything that that data structure is going to be responsible for. And so, as an example, back here, commit relative. So we basically, like, as in the relative position of, like, the very start of the stack is just 0, right? So I'm just going to say, this is getting a little cramped, but I'm going to say relative and absolute. So let's say the position here is, 16, right? I pushed a 2-byte thing onto the stack, and so now the relative position is now 16. But let's say if, for sake of argument, there's a pointer here, and it starts at 0, and the absolute position of, where I push this, of this position, is going to be 0x00, what's 16? Yeah, F. 1. Is that right? 1, 0. Yeah, I think so. Yes, that's correct. I think. So, yeah, a basic arithmetic just escapes me. And so the benefit of this is this right here can be, like, anything. You know, if you have a very small stack, like if it's like only 255 bytes, then the offset can be a single byte. And if it's less than 64K, then it can also be a int16 or just a 2 byte. But a pointer is always going to be, you know, like 8 or 4 bytes, depending on the architecture. But the thing about a pointer is if you dereference it and it's null, you get an exception, right? You'll crash the program. An offset cannot be null, right? So this is like, instead of storing this, like this right here is what you want to store. So we store offsets. And so then I basically have arena get pointer, and it just takes in a const u32 offset, right? And if I know the offset of like whatever object I'm getting out of there, it just looks it up, and it can also say, hey, Mr. Programmer, your offset isn't valid for this arena. And so you may be able to turn these offsets into more opaque handles. Like, for instance, if I have, like, asset handle, and I basically store the arena that it was allocated from, which, again, remember, it's a handle, which is 32. And let's say in this arena, I only have, it's only 65. Or I just can say, you know, I store another 32, and it's just offset, right? So then a handle for a specific object I want to get now becomes which arena was it, and which, you know, where is it inside of the arena, right? And so then we've sort of, I hate to say abstracted away, but we've introduced this concept where we don't have to worry about getting null pointers back. If we did the check up front to get this arena, and we know ahead of time that the arena is valid and the handle's valid, we don't have to worry about null pointers. See, that is the power of doing something like this. And also, these right here are cacheable, right? And I'll go into this in a little bit, but let's say if I had a ton of pointers, right? Like this is a normal, like, example, right? Let's just do this. Example with a tree. So we have node up here that goes to, you know, these nodes. We'll just say it's a binary tree, right? So we have nodes here, and maybe a node here, and then this one right here has another 2 nodes, like that. So if each one of these are pointers, and they were stored on the heap, like, we already know the issue with the heap, but let's say we were just, we have an arena and we're dividing it up. So each one of these is a, you know, it's a pointer. So I'm just going to say just 0x for pointer, 0x, 0x, which is like, you know, 64 bits of information times however big, like however many nodes that are in, like, we'll just say count nodes, right? Sorry for my deplorable handwriting here. But let's say this. Remember, in a data structure, we have a start and a finish, or a start and a size, right? So these are the 2 things that make up a data structure. As in, if I start here and I advance this far, everything inside of this data structure is going to be found within this chunk of memory, right? But let's say if this data structure is like less than or equal to 64K, right? 64K can be like any, a number up to 64K can be represented by a U16, aka short, aka 2 bytes, right? So remember, 64 bits versus 16 bits. We've now quartered the size of a single node. And so now, if I have like 1, 2, 3, 4, 5, 6, 7, 8. So 8 times 2 is 16 bytes. But I have, let's see, and I guess we can just multiply that by 4. But basically we have, you know, something that looks like this versus something that looks like this. Let's see, 1, 2, 3, 4. I guess, you know, 5. So I'm terrible at this stuff. Doing math on the fly. But I think that's right. So this right here, and I think my daughter's laughing underneath the door. She is so adorable. So basically, you can store an array like this is much better. And while this will work, I don't want to... It's like one of these weird, like, check X things where it's like, this will work, but, like, this right here is the superior way to do it. If you are searching, like, if you're iterating through keys, you can fit a massive amount of keys in a small amount of space versus, like, the information density is much, much higher in the one up top. So that's the reason I like to use offsets. Yes, a hit on an offset you actually want, like in retrieving that pointer, will most likely be a cache miss. But if you're iterating through something, like if I am accessing this, the most common operation is I'm going to need this as well. And if I have that, I'm going to need this. And if I have that, I'm going to need this. Like if you're just iterating through an array, right? Because that's how a cache line works. It's just basically an array of bytes. And a cache line is usually around 64 bytes, I think. So it's just a way to make sure that that cache line is packed with the information that we need. And that's just the reason why I'm using, you know, the concept of offsets and indexable data structures versus storing raw pointers. But now we come back to the question up here of, like, you know, how the hell do we actually manage one of these things, right? And so that's with allocators. And there's two main types we're working with. Two allocator types. And we went over this last time. So I'm not going to be spending too much time. So there's linear, and there's block, right? I may have used stack last time, but we're just going to say linear, right? And so linear is essentially a stack, right? I've explained this until I'm blue in the face. It just basically has, you know, push bytes, pull bytes, reset. But this one gets a little tricky, right? So we have a position as before, but it changes a little bit, right? We also want to say save point. As an example, let's say if I have a user interface, right? And I'm pushing strings onto it that represent the options in a menu. And you go down into a menu and into a menu, and let's say when you go back and that menu goes away, we can just reset it back to that save point before we pushed all of the strings onto it. So that's just essentially how a linear allocator works. It just basically burns through and then resets. It's kind of like an accordion, right? It just it grows and it shrinks. But it only goes one way, as in, like, it has a fixed start and a position that can go up and kind of come back down, like it can stretch and squeeze, right? And a block allocator has fewer controls, but it's slightly more complicated to manage, but easier to understand. It's a little weird. So a block allocator is essentially just an array of just big, like, you know, chunks of memory. So if I say I have a block allocator and it's divided into, let's say, I'm going to say b sub 0, b sub 1, and b sub n, right? And what it does is each one of these, like, we have a block size, like we have b size and b count, right? And so n over here is like n minus, or n equals b count minus 1, right? So essentially what we do is we just have to store information about, like, how I like to do this is if I'm returning a pointer to this block, and this is actually when, yes, I'm actually going to be returning pointers in this case, because now these are allocators. So, or rather, I can choose to return an index or a pointer, something. It just has to store, like, which ones are active. And how I like to do that is I just say there's, like, block addresses, right? And it'll actually store, like, what is the address of this block if it were to be reserved, right? So if I just pass in, like, go to, like, in block, and if it has an address of 0 in it, it's free, it's available. If it's not 0, then it's occupied. And so I can just say, you know, reserve me a block, release a block, so on and so forth. And same over here, it will also follow this nomenclature. Because it's not really a stack, it operates like one. Like, it has the same concept, but we are using the terms of reserve and release, because these are resources that we are borrowing and releasing when we're done. But so basically, here's a summary. And I know that I'm kind of all over the place with this. But here's a summary. We reserve virtual pages, which is, you know, this over here. That's like step 1. Step 2, commit arenas. Which is going to further subdivide that into regions of memory. So A sub 0, A sub 1, A sub n. Commit allocators. So we can say, and also an arena, you can also just push and pull bytes, or reserve and release bytes, because they also have a position. So we can just bump that along, but our allocators are fixed for the life cycle of the arena, essentially. So we have, like, we can say we have, like, alloc for S for stack, and alloc B for that, and then we just have free space that we can use, and then 4 is reserve and release contextually, I guess. As in, like, you know, I've got this right here, which could be, I don't know, GUI text. And then this right here could be asset data. It's whatever you want it to be. The world is your oyster. I'm just going to say R sub 0 for, like, reservation up here. But you can sort of see this hierarchy happening where all of this has been pre-allocated, right? So what we're doing is we're just continuing to subdivide a very large region of memory into smaller and smaller chunks that are managed by, you know, a certain system. It could be vertices in a renderer. It could be, you know, assets in the asset system. It could be files. It could be anything, right? This is just how we're using our memory. And so with that, let's actually start taking a look at some code. So let me go ahead and just minimize this. And let's see. So what we've got here is a memory context, like we said before. A context is just, it's something that's going to store information about the platform, which is like how big our page size and our allocation granularity is, and allows us to get information about, you know, what sort of memory constraints are we working with. I may even, I was about to say put cache line information in there as well, but that's more of a CPU thing, not really a, you know, memory management thing. So we can see that, you know, like here's something I was talking about, right? So when we create the context, we just pass in a static array of bytes. And in this instance, it's going to be initialized to 512K, right? So, and what we want to do is we want to push stuff onto that stack. And we have two options. Committing something relative will just get us the offset of where it was in the stack, and then committing something absolute will actually get us the pointer to that data we just committed, right? And then we move on to reservations. Now, for I'm thinking for this entire game, we're only doing one reservation, unless we have some sort of like external tool or profiler that we make that like launches in a separate window and then attaches to this. So we may just say, hey, I'm going to make a reservation for this tool that I need to launch. It'll have its own memory, and then we just, when it closes, we cut it loose, and then we're done. So from there, we can commit arenas to the reservation. Let's see. No, we don't need that, because we start at the context and then reserve stuff. And then with the arena, we can push bytes onto it. Like, we can just use it as a simple, you know, sandbox to just push stuff onto, like a stack. Or we can commit allocators to it, right? So, and I'm starting to see where this could be potentially a problem. Yeah, we may want to do something like, I think I've got it. So, what we could do is, like, let's go over, like, arena architecture, right? We could have two stacks inside of this thing. So what we can say is we have two stack positions. One that basically goes let's see, bottom, top. And this part right here goes bottom to top, and this one right here goes top to bottom. All of you centers, get out of here right now. So, and this is a commit position. And this is a reserve. Or committed. Excuse me. Just a moment. My apologies. So, basically, this is a reserved position. Yeah, I think I'm going to do that. Because what we commit, we don't want to release, right? So we can just say, this is going to go from here down, but then it may just need to be the opposite. I mean, we'll figure it out. We're just basically kind of scaffolding and getting an idea of how this works. This is why I like C++ so much. And C, for that matter, because you can sort of, like, define, you could sort of like define the data and start thinking about the operations that need to be done on that data. So you can separate your data in your code so it's more like C style syntax where I have structs that define data. So like this is an allocator sub 0, allocator sub 1, allocator sub 2, and then this up here is just scratch space, right? And so I want to make a temporary thing like, shit, I need to do a quick allocation to do like a computation in this function, and then when I'm done, I'm just gonna like put it back onto the arena, right? So that's essentially what scratch-base would be, is like, you know, I am doing, like, I could see this being useful in like collision detection and other like math-intensive stuff like inside of the game that are like outside of the engine. If like something happens, like the little Jorm character's running around and like he's slingshotting around and there's like all these calculations that are being done, if I need to like do some quick allocations to do some math, and then I churn and burn, return those bytes to the arena, and then we're done. So I could see that being useful. So, yeah. My ADHD having ass is struggling today. So, with that, so we know that's how reserve and commit work in an arena. And so, let's see. And so we have the allocators, right? And so, just like we said, you have the option for a save point, which you can set and you can clear to a point that you've already been to. You can reset to the beginning, or you can reset to the save point, and you just push-pull, and, you know, here's some options to get pointers back. And the block allocator, the control for that is very, very simple. It's just, you know, hey, I want to reset, meaning all the blocks in this allocator are available now. They're all free. Level start, all the asset table's cleared except for, you know, stuff that we reuse, and then we can reserve a block and release a block. That's pretty much it. And the like block allocator, I think this should be like reserve block relative and reserve block absolute, just to follow our convention. So relative would be IFB U32, which in this case would be the probably just the index of that block in the arena, or in the allocator rather, and then I don't know why, but this convention for the block allocator, it's like you have these words here like that are like sandwiched in between the word block. I don't know if I like that very much, but it is very descriptive, right? I don't know if I want to add control for reserving a specific block at an index. We can, but I mean, what is the likelihood that that's going to be a common operation? It's probably not. So, but we do want to say, like the same convention down here. If I, am reserving, yeah. Or here, I'll just say this. We got block memory and block offset that we want to release when we're done with it. And then the info is just like, you know, hey, we probably don't need page start and size. That's not really information anyone's going to care about. Total size, block size. I like to... yeah. And we don't need this. It's trivial to calculate that. Like, try to... one way to save on memory is, like, to... don't store things that you can easily calculate. Because like, it saves on memory, and it also, there's just more stuff that you have to update, right? There's more stuff you have to keep track of in the struct. Can you close this damn, split pane, please, VS Code? I did not want you to do that. But we have this internal file, which is like, what are the actual definitions, right? So we can go up here, and a handle is just basically an offset. You know, we have this offset here that is relative to some start point, and that's it. So we have these handles for reservations, arenas, and inside an arena, we just basically say, here's our parent reservations that we were made from, a handle to myself, and a pointer to the next arena, because we're basically storing these in a linked list. And we push things onto the stack. Yeah, this is going to be a terrible video, I know it. I'm just all over the place, but it's okay. I'm doing this live, and it keeps me focused. So we have a stack, and we have the offsets, right? So, for instance, I have this big information structure, right? And it has these large numbers in it, so 64-bit / 8-byte numbers, and just a bunch of numbers that is, just information about my, like, how I'm using the memory. Well, rather than store that structure inside of my context, or even a pointer to it, just store an offset to where it's located in the stack. And that's it. And this is going to be a little different. Like, let me show you how, let's see, main.cpp, right? So here's the main file, and this right here is my stack, where it's defined. So I say, I want to allocate a 512 kilobyte static array that's on the program stack. And it's initialized like this. It's just a simple array of bytes, which is, remember, just single byte, a whole 512 times 1024 bytes wide. And that's how we initialize it. And inside the context, the engine context, is where we actually initialize the memory. So the goal for tonight is I just want to get this thing compiling. That's pretty much it. So I've been tearing this thing up, ripping it up and rebuilding it all week. So let's go ahead and start coding again. So I think memory.hpp, and then what do we have? We have the memory context, right? And I'm going to put that over here. So what we do is we have our stack memory. We cast that to our context itself. So basically at the 0th position in our stack is our memory context itself. So I have a stack start and a stack end, right? There's a... You know what? I may just remove that because we don't need it. Because like I said, it's trivial to calculate something based on, like, if I just say start plus size, there's my... there's the end of my stack. So we don't need to store that. And how I like to do this is I just say, I'm going to put together an array of sizes for the information, the reservation list, and all those kinds of things. We have this array, and I do essentially one big commit. No, what I do is I just go through the, stack and grab the, why can I not think of it? The offsets as I'm going through it. So that's the stack allocated. Then I just get the system information, which is mostly going to be needed for making reservations and committing arenas and stuff. And that's pretty much it. So alignment is just making sure that everything we do is aligned on a page boundary. Like we see, relative versus absolute. So I've already explained this multiple times. This is mostly me just kind of going through it and making sure that everything is in, like, should be here. But here's an example. Like, I've already pushed the reservation list onto the stack. And if I go to memory internal, we can see that the reservation list is just essentially a linked list. It stores the last element, and how many. I do make an exception for count of things. Oops, I moved my editor. But yeah, so I don't have to walk a tree of pointers to count something. It's relative. All rules are made up. Fuck it, do whatever you want. Nothing matters. Do as I say, not as I do, right? So what we're gonna do now is work on the reservation. And I have done all kinds of nonsense to this. So I don't really know what I want to do. Oh, right. I moved it to the context, right? So if I go to what was it? Memory.h. And so I'll say reserve and release platform memory, right? So that's what we're going to do right now. Okay, and I think I need to fix a definition for the stack as well. Let's see, context get pointer. Yeah, that's going to be called context stack get pointer. Yeah. Context stack get pointer. We don't need that anymore, and we can just say reservations. I have no idea if I'm going to get this thing compiling or not. And honestly, we don't really need our allocators tonight. We're mostly just getting the engine running, right? And I want to move over to the engine so I can show like how this is actually used. So let's see, IFB memory. We want to initialize that. So, man, this synthwave music is popping. I love it. I love it. My wife hates it, but I love it. Let's see, context memory. We got the reservation handle. So what we're gonna do here is, first, we need to get the information for the, which is really simple. We just say, get the info, context info, and what we're gonna do is get the granularity. Yeah, that's what we need. Get the granularity. So the allocation granularity is just basically whenever you tell Windows, hey, I want you to allocate this much memory, what it'll do is it'll align it to the next multiple of that. So we say granularity, in system granularity, and this should always, if we are calling this at this point, we should always have this. So we're just making sure it's not 0. And align the size. Let's see, size aligned equals, let's see, macro align A to B, size minimum to granularity, right? And so then we want to make the reservation. So that would be, so the platform API will have memory reserve, but it'll have the definition for like how we do it in Windows. So it'll be size aligned. And so this is going to return a pointer, I believe. Yes. So so we do the memory reservation, and we are, if that fails, there's nothing else we can do. So like if that fails, we're just done. Return a, actually, I can go ahead and just make this right now, because this is our result, right? Reservation handle. I'm just going to say ND reservation. No, I'll spell it out if that's less obvious. Then pointer. Reservation handle. And right now we're just saying it's 0, right? So if this fails, like, we're just going to return it. But if that did work, oh, I forgot to do something. We need to allocate something onto the stack. So, we can also do this, like as an additional sanity check. I like to call it sanity check because it's like, it's pretty self-explanatory. Like, if the user said, give me an allocation of 0, like, that's just dumb. We're not gonna do that. It doesn't pass the sanity check. So, but what we need to do now is say, I need to push a reservation structure onto the stack. So, is this memory internal? So if I go to memory internal, this is what a reservation looks like. So I need to actually push that onto our stack, right? So commit reservation structure, which is going to look like this. Context stack commit. Which is going to be commit relative. And I can just say const fb u32. We'll just call it an offset for now, right? Because that's what we're getting back. And it's going to be a aligned size of our reservation structure. And we'll just say struct size. I like to be verbose. I don't like it to shorten things too much because, like, if you've got a function that's like super long and a lot of stuff is abbreviated, you can sort of get lost and lose context of like what actually is going on. So IB macro size align struct, which just basically aligns the struct to the nearest power of 2, essentially. So, there may be some compilers that do that automatically. I don't know, but I know that this is a surefire way to make sure that everything is aligned by a power of 2. We want to do that. Align size struct to reservation, like that. And we want to push the struct size onto the stack. Do I have that right? Yes. So, okay. And if that failed, we're also done. Like, this shouldn't be 0. Like, if the struct offset equals 0, then return. Actually, stack commit relative should throw an assertion, because if we run out of stack memory, we're in a sorry spot. Yes. So that should never come back as it should never return 0, essentially. So reservation structure, we push that onto the stack, but we also need the pointer, right? Here's where we can do an assertion. We want to get the reservation pointer, get the struct pointer. Go over here. Oops. Go back to internal. Okay, and then we want to say IP reservation pointer reservation is going to be IP memory context stack get pointer, and that's going to be to this offset that we've just created. Now, here's where an assertion does make sense, right? Because we're basically, this is also why I hate unit tests, because like with the heavy use of assertions, you don't have to do this complex tree of like, oh, did this scenario happen and that scenario happen and this scenario happen? It's just like, I know for a fact that, you know, I did a commit here to the stack, and if I made it past this, as in the thing I just committed can fit, and I get a valid handle back, like, if it couldn't fit it, we get an assertion. Like, as in, it'll crash the program, and we know that, you know, that didn't work. So, if I've made it to this point, right here, I know that it fit on the stack. So now, I just say, assert that the thing we know just did worked, right? Because the assertion is, if I successfully push something onto the stack, I should always, always, always be able to get the pointer to it. So, and there's no like, if this failed, return, if that failed, return, it's just like bam, 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 bam. No unit tests. Unit tests are done. So, we make that assertion that we've got the pointer, and then we actually do the, we do that. So, honestly, because this leaves us in a weird spot, because what I may also do is do an assertion right here, because all of these things have to work, right? I can't undo a commit. Or I could make the reservation and, like, because the platform could say no, right? Like, for instance, if we have some type of platform logic where the user or the programmer who's implementing a custom platform for the game, let's say if they have to do something like, you can put in a request to reserve something, but it fails, but make it again and it might work. So we don't immediately want to throw an assertion because this didn't work. So what we can do is just do the opposite, right? So we do the reservation first, and then if that worked, then that's when we want to do the assertion, right? We only do the assertion on stuff we know should be static and we know should absolutely never, never fail. So we have the pointer, we have the reservation, now we can initialize it. So how I like... hate it when I do that. Alright, so now what we can do is we can just say copy all of this, right? And what I may do is also make this a handle. Yeah. I may just say, let's just keep on trucking. So we can always optimize it later. But what we've done by doing this is, because like the idea is I have this arena list similar to the reservation list in that, you know, I have, here's where it's just a linked list of arenas. But do I want to make this like a handle that I store inside the reservation? I don't know, but that's something I can always do later. And that's why I like coding this way, is you can just sort of like play around with your data structure definitions, and your function definitions don't really have to change, but you just have to change like the data transform on it. So we have that, and so we just say initialize the reservation, right? Oops. So I'm gonna line everything because I have OCD like an MFer, and we're just gonna say, let's see, I know that's not valid on some platforms, but, you know, we can always fix that later. The next reservation is null because we haven't added it to the list yet. And the start, I like to store the, oh shit. Let's see, because I did this reservation up here, so I have two things that are named pointer reservation. I'm gonna say pointer result, right? Pointer to, or I can just say pointer, the pointer to platform memory, right? That works. So what we can do is I can say, and an address is just an integer. That's another way of thinking about it. It's a, when you're doing a pointer arithmetic, like if you're doing a lot of math on pointers, it can be a little bit more efficient to just store the numerical representation of that pointer. And also, these are, they can't be dereferenced, so you add a little bit of security in there too. So the stack offset would be what we have just made, and wait, what? Stack offset. I think I'm just gonna say handle. Right. So we've not H and F, H and D, and that'll be, you know, handle. I may just... Nah, we'll keep it. So this is what we're returning, essentially. And that would be the reservation handle that we've just made. And then the handle, set the handle offset. You know, we may just be able to kill two birds with one stone and say reservation struct offset, reservation handle dot offset. Yeah, I think that's what we're gonna do. So we can just say this right here. Offset equals that, right? And so that's done. And we say, I want to get the pointer to the thing that we have just made. And that's going to equal the reservation handle, page size, count total. Is that really necessary? Yeah, so one reason I like to sort of divide the pages like this is so I don't have to store a single 64-bit number. A 64-bit number like that can sort of like throw the alignments of the struct out of whack, and the compiler may just add extra padding. I like to know these things. So what I can do is say this page size. So equals that, and pointer info dot page system page size, right? And so oops, no, this is good. Okay, so what we can do is calculate page size. Okay, or calculate page count. And so we've already aligned everything, so it should be safe to do this. So const 32 page count is going to be the size aligned divided by the page size. Oop. Page size. And we can just yeah, it's okay. I sort of like putting calculations in constants like this because it makes it very easy to debug. And if you as long as you're doing like sane declarations, the compiler, if you have optimization flags turned on, they can sort of like fold this math together without doing like the explicit declarations of stuff sometimes. I think it just depends on how complex it is, but it just makes it easy to debug when I do this, and if it's a problem later, we can always just sort of fold those calculations down. So I think, by golly, that's it. So we're done. And we're going to return the reservation handle. Right? And that's it. We also have to add it to the linked list, right? So what we're going to do is say add reservation to list. So, and this is real easy. So the reservation list, let's see, context, get reservation list, right? Reservation, and I already have an assertion in there. Reservation list, right? And what we're going to do here is say if pointer reservation list like if this is the first one, right? If this is the first one we're adding to the list, first I want to do this is also another useful thing where asserts happen, is I know for a fact that all the pointers should be null, right? So, shit. As in, like, the first and last should be null, right? Equals null. So we've done that. And so what we're going to do now is just say the first is going to be what we've just made. And the last one is going to be the same, right? And then we just say the count is 0. That's it. If this is the first one, we need to initialize the list, right? pointers should be null, and then initialize the list. Actually, that should be 1. Otherwise, and I think we can say, we're done. Or I could just say else. We got a little bit of work to do. I don't know why. I don't like putting return statements inside of else statements. I like to put them outside of it. I like to have like a very clear path through a function. So, otherwise, what we're doing is this pointer should not be null, right? The first one, we definitely need it to be. So, first element should not be null. But if the count is 1, right? First and last elements should not be null, right? Because we know that they're initialized. But, big but. So we know that if this is 1, if the count is 1, this one right here, first dot, what did I do wrong? Compiler, what did I do? Pointer reservation list. Where are you angry with me? I don't know. But, basically, the next in front of the first one. Come on, you bastard. Yeah, so first dot next. Right? So, I'm violating one of NASA's powers of 10 rules here, but that's okay. As in, like, only dereference pointers by, like, have 1 layer of dereferencing. But what we're essentially doing is we are making sure that, like, this one here is null, right? But then we can just move on to adding that, which would be pointer reservation first dot next. I'm just going to dereference this. So first element be reservation second element equals, or no, it's going to be like this. First element is that, and we're going to say that we've already asserted that that's not null, so it's safe to do this if we get past this point. So that should be null, but we need to, if this is the, if we are adding a second element, make sure we update the next pointer for the first element, right? So then what we do is we say next first element dot next equals pointer reservation, right? And then what we can do is say pointer reservation list dot let's see, cache first and last element. Last element is gonna be last, and so what we can do is say so last element dot next is basically we're just adding this to the end, right? So pointer reservation that we just made, and then now in the reservation list, the last element is now our reservation we just made, and we are also going to assert at this point, we always know now that the first element should have a next one at this point. And so update the end of the list. We update the count. This is why I hate linked lists. Like, they're convoluted, but there should not be that many reservations here. Where reservation list account will be updated. Now, if you're a keen observer, you may have noticed that, like, we have a list of reservations, and a user can just continue to grow this list by making reservations, but if they release them, these things are committed down to the stack, so we are not going to be reusing them. So right now what I'm going to do is just put a to-do statement here, is say to-do, not tofu, to-do, let's see, make sure we search the list, not the list, the list for released reservations to recycle, right? So, this will work in a pinch just to get us up and running. So that was really convoluted. But what we want to do now is say context. Do I have a thing to get reservation pointer? Let's see, I could say get reservation. Go like that. And sort of put that down here. Right. The memory context get reservation. You know what? I think I'm just gonna delay partitioning the arena list because it's gonna be a lot of hubbub doing the same stuff. Let's see. Let's see. I think I'm gonna be running out of time. So I know that this is already long-winded, but people wanted to see this apparently, so here you go. I am happy to oblige. Let's see. So what we want to do is say first get the stack. Let's see. Like basically get context get pointer. No, that should be oops. No. Context stack get pointer. That. And it's gonna be reservation list. No, it's gonna be reservation handle.offset. That's basically it. I love synthwave. As I've said before, pointer reservation equals that. This isn't going to be compiling tonight, but next time I should be past this. But I don't want to bore everybody to death. I love this stuff. I could just do it forever. But I know, like, bitchin' memory allocators is not why people play video games. So we basically get the pointer to that, pointer reservation. We know that we should have one, so what we're going to do is say we're done. And I just put that there. It's just like, am I putting way too many words and stuff? Yes, but it's also just really easy to follow. And it's like, because I know my ADHD having ass is going to be forgetting sometimes what I was trying to do, and I just try to make this as plain as possible. So what we do here is we say IFB reservation, and we say pointer to the reservation equals this, stack get, no, context, stack, or context get reservation, right? And so it's going to have that reservation handle, and just say, you know, we've already asserted that that's not null, and we first of all say memory, or no, we want to tell the platform, hey, Mr. Platform, I'm going to need you to release the memory that I have acquired. So, and the pointer to start is going to be const, be a pointer reservation start is pointer reservation start, and remember that's an address. We need to cast it to a pointer like this, and we also need to put together the size again. So, which is a big number, wumbo number. Reservation size is that, and it will be pointer to reservation of dot page count total times I may just end up hashing the page size somewhere, because the amount of queries I have to do with how I've abstracted this is just kind of ridiculous. So, oh, I forgot to do something. So, if you assert one, assert the other. So here, we're just going to copy that, and, let's see, get the reservation, and we want to get the page size. We don't need the granularity, just the page size. And it's going to be times page size, right? And like I said, I may cache the page size in there because I'm going to need it. I can do that later, though. To do. I'll put that over here. Block allocator. No, that's not correct. Just keep going. So what we're doing is we're just basically releasing this memory that we have acquired previously, and we're just returning the result, right? Result equals that, and we just return result. And like I said, the reason that we don't necessarily want to assert on this is because operating systems are fickle. They may or may not just flat out refuse to do something. But that doesn't mean just, panic and give up. It just means you may have to try again. So I know within the context of what I'm doing that that shouldn't happen, but yeah. Calculate reservation size, release memory, and we're done. But we have something we need to do first. Let's see, update, not update the reservation. And what we need to change over here is the, let's just copy this. Arena list can basically be milled out. Next is fine. Handle is fine. As in, we don't need to update that. We don't need to update that. We're just basically zeroing everything else out. Pointer to reservation. So what we're going to do is say update that, and we transform this by just zeroing everything out, right? These are irrelevant. Wait a minute. I may have to store the arenas separately. Yeah, I'm gonna have to do that. Because they are also committed onto the stack. They are not... yeah. It's okay, though. Basically, everything here is just gonna be zeroed out, right? And we're done. And I'm just gonna say commit that because that's pretty good. So, let me go ahead and, to wrap this up, sort of like show... This is not a memory manager, right? It's just like a context for how... I'm basically giving memory usage context, right? This library is just a tool, right? That sort of helps me give context to a stack and some pages of virtual memory. But where that context is applied is in the game engine. So, I think it's like engine context. So, what we do is we have an engine core, right? Which is sort of like, it handles how resources are divvied up amongst the game engine. So, if a system needs a file or a memory or a thread, it will basically send a query to the engine core that says, hey, this is what I need to do. Please give it to me, And if I go here and just say internal core, this is our engine memory. So we can go here and say, I don't need that anymore. I shorthanded this to reservation. Engine core, memory reservation, and the stack, right? So this is essentially the stack that we were passed from the main function, and I made it a local. Let's see. Yeah. So this buffer right here has the exact same address as this right here, because that's just how it's initialized. And this works because, I mean, it doesn't really have to be made, it doesn't really have to be made a static. Remember, this right here is just a scope, right? Excuse me. It is, there's like multiple different meanings to the word static, so I help give it some context as to what's going on. But it's essentially just this array that I define in the main function and where the main program loop is executing, And that works because this will never go out of scope. And the local just ensures that it, it's just giving more information that says, I want this allocated on the program stack, and, it'll be allocated on the program stack anyway, but it's just saying, this is going to stick around for the entire lifetime of this program, and just giving the compiler as much information as possible. So, I've got this core memory stack and the core memory reservation, and it's just essentially mirroring what we've had there. I'm going to do some... You see a lot of the similar things in there, but it's essentially wrapping around the functions that we have defined already. So if I go to core memory, it's just essentially just wrapping what it did, right? And what we just did. We make sure handles are valid, we get the information from our reservation, and we just store it that way, right? So... And then this is where we are going to be doing stuff with arenas, right? And I can also... What I want to do is to sort of minimize the headache that comes with how much do I want this arena to be. I'm going to find my own arena for the engine. Right? So an engine arena. And we'll just, AP, H&D, arena. And a stride. So what is a stride? Well, a stride is just basically a multiple of something. And what's that going to be a multiple of? I'm going to say... I hereby decree that the minimum size of an arena, that might be engine core memory arena size, is going to be, like in kilobytes, 64. Right? And so, when I say arena commit, and again, this is just me. I was just kind of like fucking around here. Not really doing anything too important. What I'm going to do is say core memory commit arena. And that's it. And this sort of lets me know, essentially, how big this thing is in multiple of 64 kilobytes. And it's just a really easy way to not have to do a ton of math, right? If we run out of memory in an arena and we hit an assertion, we basically kill the program, update the stride by 1 whenever we want to allocate something. Or we could just say that... I'm thunking. We could just say this for now, right? So, core memory and core memory arena size. You know what? Let's spell it out. We'll just say IFB macro size kilobytes 64, right? And we can essentially do that. That commit absolute. This also gives way to how I like to use singletons. And I know I'm going all over the place, but like what I do here in the context, or engine context rather, let's just look and see how the engine boots up, right? What happens? So remember when I talked about singletons, right? So there's only one of everything. So I've got one instance of the engine configuration, one instance of user input, my dev tools, my graphics manager, and I can also say like renderer, right? Do I want to call it a manager? Well, I'll just call it a renderer for now. So, or rather, rendering system. Why not? Renderer, like rendering system sounds better than that. So the difference between graphics manager and a rendering system is, so graphics manager manages stuff like the window, graphical, like the GUI, graphical user input, and like monitors the refresh rate and those kinds of things. And the renderer is the one that actually packages buffers up and sends them to the GPU. That is the difference. So what I do is I create an instance of the core, which what we saw, like the core, the crux of it, the heartbeat, of that for now is the memory, right? So we were passed in the memory pointer. We're also forgetting to set the API. Hang on. IP platform set API, and we want to do this, right? And if that fails, IFB B8 let's just surround that in an if statement. If that failed, we're done. We know this isn't null at this point, so we can just say we can successfully cast that to void because we don't need it. Right. So we're just casting that to void to say I am aware that this returns a boolean, but I don't need it. So I think that should work. What we want to do is commit our singletons. And so engine singletons core memory commit struct. So we basically push onto our stack, the one that we just created, a singleton struct. This, right here. So notice this buffer is pretty tiny compared to the one that we have created. So it's 64K, I believe, which is a lot smaller than 512. Citation needed. But essentially, we've further compacted this, and now I can say, if I know that everything should be able to fit in here, then everything can just be a int 16. So we've now reduced the key, or rather a handle. Sorry, I've just got something itching on my nose and it just will not go away. But that's essentially how this works. And that's just on boot up. We're just partitioning out the stack into our big engine systems. And on startup, we'll make our big, massive Wumbo reservation and start dividing that into allocators. Or arenas and allocators. That's basically it. And honestly, you know what? I think for now, if I go here, let's say if I go to engine internal core, we are going to remove the concept of an engine arena. We are just going to say that, we're going to return this, and we're not even going to have a stride. For now, we're just going to say that every arena that we commit is going to be 64K. And, that's essentially it. I can't really think of anything else that needs to be done as far as showing how we give context to memory management. That's essentially what allocators do, is we are providing context to a pre-reserved block of memory, just with how we're doing this. So, Mike Acton in his data-oriented design talk always talked about, it's all about the context of how things are done. So we're not going to be pretending like we have no idea, like, oh, it could be this or it could be that. We know for a fact that, this is what we're working with, right? We have this big chunk of memory, and whenever we commit an arena, it's going to be a sandbox of 64K. And if for some reason that's too small, then we know that we need to have multiple arenas. We'll just basically commit them back to back, right? And that's pretty much it. I don't know why that's showing up as, like, invalid syntax. Oh, because that's not right. That'd be void, right? Yeah, there we go. I sort of redid the convention for my primitive types. But that's essentially how it's going to work. And I've been wanting to make this video for a while just to talk about this, but now I can finally get to it. So I do appreciate those that have been watching. This one was a bit of a mess, but last time was a bit of a mess, and surprisingly people liked it. So I do appreciate everybody watching. It really does mean a lot. So thanks everybody for watching, and I'll see you in the next video. I'm hoping next time I've actually got, some progress, and I'll actually, the goal for next time is going to be like graphics, right? So we want to have this window up and running with an OpenGL context and refreshing. This is stuff I've already done, but this has just been like a never-ending like refactorization hell. And my devlogs for doing this is sort of to help keep me on track and say, next time we're going to be doing graphics. So we're actually going to be, we're going to have an arena for a graphics manager, and it's going to be linearly allocating stuff to that arena, just pushing stuff onto it, basically. Like, here's a window, here's graphical user interface, and here's the monitors that I have attached, and all those things. So my dog is tired of being locked in this room with me because I'm boring. So I will see you guys in the next video.